So this is the second project for the final. I'm looking at the main program. I ended up putting the functions for figuring out the lowest common ancestor for two values in the binary search tree class. Um, so here is just my basic output, so you know what's going on in the console. I have I populated the binary search tree with the values that were given in the assignment, so that's all here. And down here, I'm just I have an output to display what that binary search tree looks like for just reference purposes. And then down here, I am finding the lowest common ancestor in the tree using the method that I just explained that I put on the binary search tree class itself. So I'll run this just so it's easier to get an idea of what this actually says. So this is what the final output actually looks like. So you can see I tried to indicate the left pointers and right pointers with arrows, and then null values with X's, just to explicitly say, you know, which items are pointing to which, because I didn't want 70 to be confused about if 60 was pointing to it or 100. By putting an X here, it's clear that 100 isn't pointing to anything on the left, but 60 is pointing to 70 on the right. So that's it for that. We'll go over to this implementation for the binary search tree lowest common ancestor. I actually added two methods. I have just the one for checking if something is in the subtree or not. This is the main one though. Let's make that a little bigger and fix that real quick. So here we are taking in the two values that we want to see if or which node in the tree has them in common in their subtree. So I basically took these in and then just defined which one was the lower value and which one was the higher value. I felt like this would help my implementation later, just because then I can know which tree to go down for which value. So here I just arbitrarily assign them, and then if they are in the wrong order, I swap them. So that's all this is doing. It's pretty simple. Down here it gets a little more complicated. So I am basically trying to move down the tree, the binary search tree, until I get to the node that does not have I want the node that has the value in between the lower value and the higher value that I defined up here. So basically I want to ensure that this node is not null when I do this. I start at the root of the binary search tree. If it is null, it will skip this, but if it is not, we want to continue doing this until, and this is that condition where the lower value is lower than the value of the current node and the higher value is higher than the value of the current node. So that's all this is doing. In here, we're checking to see if the lower and higher value that we indicated up here are both higher than the value of the current node, and if they are, then we want to move to the node to the right. And then after that, if that's not the case, then we check to see if the lower value and the higher value are both lower than the value of the current node. And if that's the case, then we are moving the node to the left of this one. So we'd be moving down into the left subtree. So we will basically continue doing that until neither of these conditions really work, which means that we are at a node where the two values diverge. So one's on the right and one is on the left. And so that will eventually take us out of that while loop. And Down here, it is possible that our node pointer could be null. If that's the case, we're going to return -999, which is just an arbitrary value, to explain that either there was no root, or actually in this case, it was just that there wasn't a root. When we do have a node pointer that we want to use, we are basically checking to see if the left value, or the lower value that we defined earlier, is in the left subtree, or here, if the node that we are on has the same value of the lower value. So that will that's just one condition. And then we do the same thing for the higher value. So we're checking to see if the current node that we're on has the same value as the higher value that was defined earlier, or if the higher value is in our right subtree. So, and if those conditions are satisfied, if both of them are true, then that means that the node that we're on is the node that they share as their lowest common ancestor. So we are returning just the value of their lowest common ancestor. And if not, -999, which is like one of them or both of them are not in the tree. That's the same condition as I had down here. These in subtree methods are just calling this down here, which is pretty simple and very similar to the search method that's also defined in this class. So we take in the root node and start there and look at the value that was passed in. For our particular case, it could be either just the lower value or the higher value. It's not really relevant. We just want to know if it's in the subtree or not. So we are going to continue through this case until either this node pointer becomes null, or until we hit the value that we're looking for. And if we do, we're wanting to return true and bump out as fast as possible. And otherwise we'll return false. So if the value that we're looking for is lower than the current node, we are moving into the left subtree by updating the node pointer to the left. And if the value is higher than the current node that we're at, we are updating the node pointer to the node to our right. So as this continues, it will move down the tree appropriately, either left or right, until we get to the value that we're looking for, or we reach the end. So if we get down to a leaf node and we didn't find that value, we could move left and then the value would be null, which would mean our node pointer is null and that value was not in the tree. So that's how that's working. It's pretty easy, and I believe that covers how this entire method works. So, thanks.